Welcome, everyone. I'm excited to kick off today's presentation. Today, we're diving into the power of determinants. We'll explore what determinants are and why they matter so much. Over the next few slides, we'll uncover their impact and applications. So let's get started and discover the fascinating influence of determinants together. Let's explore some further geometric applications of determinants. We'll start with minors and cofactors, which are fundamental building blocks when working with larger matrices. Understanding these helps us analyze and compute more complex systems efficiently. Next, we'll look at how determinants are used to solve systems of linear equations, providing powerful tools for various applied problems. We'll also cover the fundamental properties of determinants, which are essential for simplifying calculations and understanding the behavior of matrices. Mastering determinants gives you a true mathematical edge, especially when dealing with geometry and linear transformations. Moving on, we'll see how determinants have real-world applications in geometry, helping us interpret shapes, volumes, and orientations. We'll also discuss how to evaluate determinants, starting from small matrices and progressing to larger ones, which is crucial for practical computations. Finally, we'll examine the concepts of the adjoint and inverse of a matrix, both of which rely heavily on determinants. And to wrap up, we'll clarify exactly what determinants are, ensuring you have a solid grasp of their significance and utility in the broader context of linear algebra and geometry. So, what exactly are determinants? Well, in our context, determinants are the various factors that influence health outcomes. They are the underlying conditions that shape a person's health status, often beyond just individual choices. These determinants can include things like socioeconomic status, education, environment, and access to healthcare. Understanding these factors is crucial because they help us see the bigger picture of why health disparities exist. By recognizing these determinants, we can better target our efforts to improve health at a community or population level. They really form the foundation of our overall discussion on health equity and how we can make a meaningful difference. Let's delve into what a determinant actually is. It's usually denoted by O or det, A, and it's important to remember that this concept only applies to square matrices, those with an equal number of rows and columns. Now, a determinant is a special scalar value that we can associate with every square matrix. Think of it as a unique number that captures certain key characteristics of the matrix. This number isn't just a random value. It tells us a lot about the matrix's properties, such as whether it's invertible or how it transforms space. So, when we talk about determinants, we're really talking about a compact way to understand the essence of a matrix's behavior in a single number. This idea ties into our overall exploration of matrix properties and their applications. Let's take a closer look at evaluating determinants, starting from the small ones and moving to the larger ones. When we talk about determinants, we're essentially assessing factors that influence the overall system or outcome. It's important to understand that small determinants, while seemingly minor, can actually have a significant impact when combined or in specific contexts. As we move from small to large determinants, we begin to see how these individual factors interconnect and contribute to the bigger picture. Recognizing this progression helps us better analyze complex situations and identify where interventions might be most effective. Throughout this presentation, keep in mind that understanding the hierarchy and relationship of determinants is key to making informed decisions and developing targeted strategies. Let's take a look at how calculating determinants depends on the size or order of the matrix. The methods we use for finding determinants change as the matrices get larger. So, we'll start with the simplest case, which is a 1x1 matrix. For a 1x1 matrix, calculating the determinant is straightforward. It's just the value of that single element. Next, we move on to 2x2 matrices. Here, we use a specific formula involving the products of diagonals, which makes the process efficient and easy to remember. Finally, for 3x3 matrices, we typically use the rule of Saris or cofactor expansion, which involves more steps but follows a pattern that we can master with practice. Understanding these methods from small to large helps us see how the concept of determinants scales with matrix size, tying into our broader goal of mastering matrix operations and their applications. Now let's look at how we calculate determinants for matrices of different sizes. For the 3x3 matrix A, which is A, B, C, D, E, F, G, H, I, we use a specific formula involving minors and cofactors. Essentially, we take each element of the first row, multiply it by the determinant of its corresponding minor, and then add or subtract those results accordingly. The formula looks like this. A times the determinant of the submatrix formed by removing the first row and first column, minus B times the determinant of its minor, plus C times its minor. This method is called expansion by minors or cofactors, and it's very powerful for larger matrices. Moving to the 2x2 case, for a matrix A equals AB, CD, the determinant simplifies to just add minus BC. It's straightforward and quick, often used as a stepping stone for understanding bigger matrices. And finally, for a 1x1 matrix, which is just a single element, the determinant is simply that element itself. So, for a matrix A, the determinant is just a. Understanding these different methods and formulas helps us see the bigger picture of how determinants work across various matrix sizes, and it's fundamental for many applications in linear algebra. Let's take a closer look at the fundamental properties of determinants. These properties are essential because they help us understand how determinants behave under various operations. First, we have the property of linearity, which means that if you fix all but one row, the determinant is a linear function with respect to that row. This property is key when performing row operations. Next, there's the property related to row exchanges. Swapping two rows of a matrix changes the sign of its determinant. This is important because it shows how sensitive the determinant is to row permutations. Another critical property is that if a matrix has two identical rows, its determinant is 0. This highlights the idea that linear dependence among rows leads to a 0 determinant. Additionally, if a matrix has a row of zeros, the determinant is also 0, reinforcing the idea that the determinant measures some form of volume or scaling factor. Finally, these properties connect back to the overall theme of how determinants encode geometric and algebraic information. Understanding these fundamental properties allows us to manipulate and interpret determinants more effectively, especially when solving systems or analyzing matrix transformations. Determinants behave in predictable ways, which is actually quite helpful when we're working with matrices. Understanding these properties makes our calculations much simpler and also helps us uncover key insights into how matrices behave in different situations. Now, on this slide, we're diving into the fundamental properties of determinants. These properties are like the building blocks that allow us to manipulate and interpret determinants more effectively. For example, knowing how the determinant changes when we swap rows or multiply a row by a scalar can save us a lot of time and effort. Overall, grasping these properties not only streamlines our work, but also deepens our understanding of the underlying structure of matrices. This is essential as we move forward into more complex concepts in linear algebra. Let's explore some fundamental properties of determinants that are really useful to understand. First, if you multiply a single row or column by a scalar, k, the entire determinant is multiplied by that same factor. This means scaling one part of the matrix directly scales the determinant, which is quite intuitive once you think about how the determinant measures volume or area. Next, consider what happens if two rows or columns are identical, or if one is just a multiple of the other. In that case, the determinant is 0. This makes sense because having dependent rows or columns means the matrix doesn't span a full volume, so the volume collapses to 0. Now let's talk about swapping rows or columns. If you exchange any two, the sign of the determinant flips. So the determinant changes from positive to negative or vice versa, depending on the number of swaps. This property is especially handy when simplifying determinants. Finally, there's the transpose property. The determinant of a matrix is equal to the determinant of its transpose. Interchanging rows and columns doesn't alter the determinant's value, which is a powerful symmetry that often simplifies calculations. These properties are the backbone for understanding how determinants behave under various operations, and they help us manipulate and evaluate determinants more effectively in our broader studies. Let's talk about minors and cofactors today, which are essential building blocks for larger matrices. These concepts help us understand how matrices are structured and how we can manipulate them effectively. When we calculate a minor, we're looking at a smaller matrix formed by removing one row and one column from the original matrix. This smaller matrix's determinant is what we call the minor. Now, cofactors take this a step further. They're just the minors with a sign attached, which depends on the position within the matrix. These signs alternate in a checkerboard pattern, which is crucial for calculations like finding determinants or inverses. Think of minors and cofactors as the fundamental pieces that allow us to break down complex matrices into manageable parts. They connect directly to the overall goal of understanding matrix properties and solving systems efficiently. So, mastering these building blocks is key to navigating larger, more complicated matrices with confidence. Minors and cofactors are really the building blocks when it comes to evaluating determinants of larger matrices, especially 3x3 matrices and beyond. They provide a systematic way to break down the calculation process, making what might seem complex much more manageable. When we talk about minors, we're referring to the smaller determinants obtained by removing one row and one column from the matrix. Cofactors then build on that by adding a sign factor to these minors, depending on their position. This systematic approach is essential because it allows us to expand the determinant along any row or column, which is a powerful technique for larger matrices. So, understanding minors and cofactors not only helps with calculation, but also connects to the overall theme of matrix analysis, finding efficient and reliable methods to handle complex calculations. Now, let's focus on a key concept called the minor, denoted as Mi2C7C. The minor of an element in a matrix is the determinant of a specific submatrix. This submatrix is obtained by deleting the ith row and the jth column from the original matrix. Essentially, we're looking at a smaller matrix within the larger one, created by removing just one row and one column. The importance of this lies in how it helps us understand the properties of the original matrix, especially when calculating determinants or exploring matrix inverses. By examining these minors, we gain insight into the structure of the matrix and lay the groundwork for more advanced concepts like cofactors and adjugates. This process of focusing on minors is a fundamental step in many matrix operations, connecting directly to the overall theme of matrix analysis and manipulation. Now let's look at how we can expand a determinant along any row or column. The key formula here is det of A equals the sum of each element in that row or column multiplied by its corresponding cofactor. So, for example, you can choose any row or column you like to perform this expansion. The formula looks like this. Det A equals 11 times A11 plus a 12 times A12, and so on, depending on how many elements are in that row or column. Now, the cofactors, which are denoted as a letter 1d6 to letter 2c7c, are crucial. They are defined as -1 raised to the power of I plus j, multiplied by m letter 1d6 to letter 2c7c, which is the minor corresponding to that element. This sign factor, -1 I plus mod j, is what accounts for the alternating plus and minus signs you see when expanding determinants. It ensures that the expansion correctly considers the position of each element within the matrix, maintaining the orientation and the overall structure of the determinant calculation. In essence, understanding cofactors and how they relate to minors and signs is fundamental because it allows us to expand determinants efficiently and accurately, no matter which row or column we choose. This flexibility is really powerful when working with larger matrices or when simplifying determinants in practical problems. Now, let's explore the concepts of the adjoint and inverse of a matrix. These are fundamental ideas that help us understand how matrices relate to each other and how we can manipulate them. The adjoint, also known as the adjugate, of a matrix is essentially the transpose of its cofactor matrix. It plays a crucial role when calculating the inverse of a matrix, especially for smaller matrices. The inverse of a matrix, on the other hand, is like the reciprocal for numbers. It's a matrix that, when multiplied by the original, gives us the identity matrix. But remember, not all matrices have inverses, only those that are square and have a non-zero determinant. Understanding these concepts is key for solving systems of equations, transforming data, and many other applications within linear algebra. They tie directly into the overall theme of matrix operations and their importance in various mathematical and real-world problems. Now, let's talk about the adjoint and inverse of a matrix. These are really powerful tools that come directly from the concept of determinants. They play a crucial role in solving matrix equations efficiently. The adjoint, also known as the classical adjoint, involves taking the transpose of the cofactor matrix, which helps us work with matrices that are not necessarily invertible at first glance. On the other hand, the inverse is what we use when we want to undo a matrix transformation, provided the matrix is invertible. Both of these concepts are fundamental because they connect directly back to determinants, giving us a way to handle matrix equations systematically. As we move forward, you'll see how these tools simplify many calculations and deepen your understanding of matrix algebra. Let's take a closer look at an important property of matrices. When we multiply a matrix A by its adjoint, or a J on either side, the result is always a scalar multiple of the identity matrix. Specifically, a times a J equals a J times A, and both equal the absolute value of A, or a times the identity matrix I. This property is fundamental because it links the matrix, its inverse, and its determinant in a very elegant way. Now, speaking of the inverse, a matrix A is invertible, or non-singular, precisely when its determinant, A, is not zero. If A equals 0, the inverse simply doesn't exist. This is a crucial point. Determinant 0 means the matrix is singular and cannot be reversed. When a matrix is invertible, its inverse, denoted as A, can be calculated using this formula. A equals 1 over A times the adjoint of A, which we write as a J. Think of it as the matrix equivalent of the reciprocal of a number, 1 divided by x. And speaking of the adjoint, or a J, this is actually the transpose of the cofactor matrix. Often written as CT, finding the adjoint is a key step in deriving the inverse, because it encapsulates the cofactors and makes the calculation manageable. So, in summary, understanding these properties and relationships helps us determine when a matrix can be inverted and how to compute its inverse efficiently, which plays a vital role in solving systems of equations and many other applications in linear algebra. Now, let's explore some real-world applications of geometry. As you can see here, geometry isn't just about shapes on paper. It plays a crucial role in many fields. For example, in architecture, understanding angles and measurements helps us design safe and efficient structures. In navigation and GPS technology, geometry helps us determine the shortest paths and locations accurately. Even in art and design, geometric principles are used to create balanced and visually appealing compositions. Throughout this presentation, we've seen how geometric concepts are everywhere around us, making our everyday lives easier and more interesting. Recognizing these applications helps us appreciate the importance of mastering these concepts beyond the classroom. Determinants aren't just abstract numbers. They actually have very real and tangible applications, especially when it comes to geometry. In this part of the presentation, I want to emphasize how these mathematical concepts can be used to solve practical problems. For example, determinants can help us find areas of parallelograms or triangles defined by vectors. They also come in handy when working with transformations, like checking if a transformation preserves orientation or calculating the volume of a parallelepiped. So, even though determinants might seem like a purely theoretical tool at first glance, They play a crucial role in understanding and solving geometric problems in the real world. This connection really highlights how math isn't just about numbers. It's about understanding the space and shapes around us. Now, this formula for finding the area of a triangle actually comes directly from properties of determinants, which is pretty interesting. If you look at three vertices with coordinates, x1, y1, x2, y2, and x3, y3, we can use these points to calculate the area. The key idea here is that the determinant gives us a way to measure the signed area based on the coordinates. So, by applying this formula, we're leveraging determinant properties to efficiently find the triangle's area. This approach is very powerful because it simplifies what could otherwise be a complex calculation into a straightforward algebraic process. It highlights how linear algebra concepts, like determinants, are really useful in geometry, especially when working with coordinate points. And as we move forward, you'll see how this ties into more advanced topics in coordinate geometry and area calculations. Let's take a closer look at solving systems of linear equations. This is a fundamental skill because many real-world problems involve finding values that satisfy multiple conditions simultaneously. When we talk about solving these systems, we're essentially trying to find the point or points where the equations intersect. There are several methods to do this, including substitution, elimination, and graphing. Each method has its advantages depending on the specific problem we're tackling. For example, substitution works well when one equation is already solved for one variable, while elimination is great for eliminating one variable to solve for the others. Graphing provides a visual insight, but might not be precise for complex systems. Understanding these techniques helps us solve problems more efficiently and connects directly to the overall theme of applying algebra to real-world scenarios. Determinants provide powerful methods for analyzing and solving systems of linear equations, revealing whether unique solutions exist. When we talk about solving systems, understanding the determinant helps us determine if a system has a single unique solution, infinitely many solutions, or no solution at all. This is a crucial part of linear algebra because it gives us a quick test for solvability without necessarily solving the entire system. Throughout this presentation, we've seen how various tools and concepts come together, and determinants are a key piece of that puzzle. They not only help us analyze the nature of solutions, but also guide us in choosing the most effective solving method. So, mastering determinants can really streamline our approach to understanding these systems. When we find the inverse of the coefficient matrix, we can actually solve the system of equations quite efficiently. The key idea here is that the solution can be expressed as x equals a inverse times b. This approach transforms the problem into a matrix operation, making it very systematic. The matrix inversion method is particularly powerful because it uses determinants to directly find the values of the variables. It's a straightforward way to solve systems, especially when dealing with square matrices. Now, related to this is Cramer's rule, which also leverages determinants. It helps us determine whether a system has a unique solution, no solution, or infinitely many solutions. Essentially, by examining the determinants, we can quickly assess the nature of the solutions without solving the entire system outright. And that brings us to the importance of checking for consistency. Before applying these methods, we need to verify whether the system actually makes sense, whether it's consistent. Ensuring that the system is compatible is crucial because these techniques work only when a solution exists. Overall, these concepts, matrix inversion, Cramer's rule, and consistency, are interconnected tools that help us analyze and solve linear systems efficiently, reinforcing the overall theme of mastering linear algebra techniques. Let's explore some additional geometric applications that extend beyond the basics we've discussed so far. These applications demonstrate how geometry is not only theoretical, but also incredibly practical in various fields. For example, in computer graphics, understanding geometric principles helps us create realistic models and animations. Architects use geometry to design structures that are both functional and aesthetically pleasing. Additionally, in robotics, geometric concepts are vital for navigation and movement planning. These examples highlight how the principles we've covered are foundational to many innovative technologies and industries. Recognizing these applications reinforces the importance of mastering geometric concepts, as they serve as building blocks for a wide range of real-world solutions. Beyond the area of a triangle, determinants actually have even more applications in geometry. They help us define and understand lines and planes in space, which is pretty fascinating. When we're working with lines and planes, determinants give us a way to analyze their relationships, such as whether lines are parallel or intersecting, or to find the equations of planes. This ties into the overall theme of how determinants serve as powerful tools not just in basic calculations, but in understanding the geometry of three-dimensional space. So, as we move forward, keep in mind that determinants are essential for exploring and solving more complex spatial problems. Determinants can be a powerful tool when we want to find the equation of a line passing through two given points. Instead of doing complicated algebraic manipulations, we can use determinants to simplify the process. This approach makes our calculations more straightforward and less prone to errors. When we apply determinants in this context, we're essentially leveraging their ability to handle the relationships between points in a very efficient way. So, by understanding how to use determinants here, we're strengthening our overall understanding of how to work with lines in coordinate geometry. It ties back to the broader theme of making complex problems more manageable with the right mathematical tools. Today, I want to talk about a key concept in geometry: collinearity of points. 3 points are considered collinear if they all lie on the same straight line. One way to check this is by looking at the area of the triangle they form. If the 3 points are collinear, that triangle essentially has 0 area. And what's really interesting is that we can verify this condition quite easily using determinants. So, by calculating this determinant, we can determine whether the points are collinear or not. This idea ties back to our overall theme of understanding geometric relationships through algebraic tools, making complex concepts more accessible and manageable. Let's talk about mastering determinants and why they give you a real mathematical edge. Determinants are powerful tools because they help us understand the properties of matrices, especially whether a matrix is invertible or not. This is crucial when solving systems of linear equations, as determinants can tell us quickly if a unique solution exists. By mastering how to compute and interpret determinants, you gain a deeper insight into the structure of the data or equations you're working with. This knowledge enhances your problem-solving skills and makes your overall approach more efficient. Connecting this to our broader theme, understanding determinants is not just about the calculation itself, it's about developing a strategic advantage. It allows you to analyze complex systems with confidence and precision. So, think of determinants as your mathematical edge, something that elevates your ability to tackle challenging problems effectively. Understanding determinants is really fundamental in Class 12 maths because it sets a strong foundation for more advanced topics. It helps us grasp concepts in linear algebra, geometry, and even beyond that. When we talk about mastering determinants, we're gaining a crucial mathematical edge that will serve us well in higher studies. By understanding how determinants work, we can solve complex systems of equations, analyze geometric transformations, and explore structures in higher dimensions with confidence. So, really, mastering determinants isn't just about excelling in exams. It's about building a critical skill that opens doors to more sophisticated mathematical ideas. This understanding aligns perfectly with our overall goal of developing a deep and versatile mathematical mindset. Now, let's talk about how to apply our theoretical knowledge to real-world scenarios. This is where the practical insight comes in, building a strong foundation that will support higher-level mathematics down the line. By understanding the underlying concepts, you're better equipped to approach more advanced topics with confidence. When we tackle complex mathematical problems, it's not just about finding the right answer, but developing problem-solving skills that allow us to think critically and adapt to new challenges. Remember, The goal is to connect everything we've learned so far to practical applications, so that you're prepared not just for exams, but for real-world problem-solving situations.